our expert, Dr. Shiva Chidambaram. He is already here. So he will deliver his talk on RCC structure by different FRP wrappings. And as I told you that he will explain something about his new techniques and technology, which maybe in future it can be used in earthquake resistant construction, basically, especially for RCC structures. So over to Dr. Shiva Chidambaram.
So very good afternoon to everyone. And my topic of presentation is seismic strengthening of RC structure by different FRP strengthening techniques. So these are the various earthquake failures you can see from this image. So this is a kind of a soft story failure. So another kind of soft story failures. If you watch this image very closely, you can identify the mistake which we have done during this picture. You can see various type of failures in RC structures. The very first image, which you are seeing here, SALA stands for improper construction detailing. Mainly because design is separate and detailing is separate in earthquake resistant design philosophy. Because after proper design, detailing is very, very important in resisting all the forces during earthquake. So this images are perfectly explains you how the poor detailing affects the performance of the structure. So in all the images, you can see the failures is due to improper ductile detailing in the near connection area, and column shear failure in the below images. So this is a formal RCC structure. You can see the foundation, beams, column, and beam column joint, slab everywhere. So in the RCC structure, the very important part is nothing but beam column joint. So in this image, you can see we have beam column joint in the very extreme side, corner side, as well as interior part. There are three types of beam column joints. One is interior beam column joint, exterior, as well as corner. Corner means always in the topmost story, whereas exterior stands for the outside and interior stands for internal beam column joints. Because whenever the earthquake occurs, the building used to deform during the ground vibration, and the joint is the most critical part, will allow the entire structures to deform gradually. If your joint is not able to carry such a large shear force during earthquake, immediately the building will fail or the building will collapse. So from the previous earthquakes, we have identified that joint is more vulnerable, and particularly when the earthquake occurs, the building should behave like the first two, that is called potential plastic hinge mechanism or ductile sway mechanism. You can see the first two images, and the first image you can see a lot of blue color points, that is nothing but the hinge point. Okay, the next image, when the earthquake occurs, your entire RCC frame should behave like this. Whereas the third image stands for your building should not behave like this. Basically, when your building behave like this, we can expect soft story failure. So during earthquakes across the world, we have identified a lot of soft story failures because of this third mechanism. Because during earthquake, your building fails to form plastic hinges in its perfect locations. That's why the failure has occurred like this. So I told you interior joint, exterior joint, as well as corner joints. So during large shear force, if your because beam column joint is nothing but beam is connected with column through a joint. So now the beam is anchored with the column at the particular joint locations. If your joint is not capable to carry the beam, what will happen? The entire beam will come out from the joint, so the entire structure will collapse. You can see a lot of beam column joint failure during an earthquakes. You can see the first one. Again, if you closely watch the figures, you can identify the mistakes which we have done during an earthquake. See, during construction, the first image, there is no confinement at all in the corner joints. Whereas when you come to the second image, you can see a column is going through a beam without any proper detailing. When you come to the third as well as the fourth, improper detailing made the entire structure to collapse. So how to construct an earthquake resistant structure? We have two recommended codal procedures in India. One is 1893. If you want to design a structure with respect to that, you have to follow this code. Now, IS 13920 2016 came. It's a very old, 1993 is outdated now. you have to follow this particular code procedure to follow the detailing procedure. The first stands for design, whereas the second stands for detailing. So I'm not going to detail about how the design carrying, because which is already explained by various professors. So now, three important points which we have to ensure. Anchorage of main reinforcement of beams inside the joint. Second one, the confinement of the core of the joint. Third one, the shear strength of the joint. These three plays very, very important role during an earthquake. If your beam is not properly anchored, what will happen? Your beam will come out from the joint. So during an earthquake, so immediately the structure will collapse. That should not happen. That's why our IS code recommends anchoring, reinforcement anchoring into the joint. That I will explain you later. So first, in this case, worldwide is accepted philosophy that is called a strong column, weak beam. During an earthquake, a beam can fail, but your column should not fail. At the same time, plastic hinges should follow in the exactly below point of the column as well as in the beam column joint location, so that we can expect a ductile sway mechanism. Because if a column fails, the entire structure will collapse. That is generally referred as globalized failure. If your beam fails, then that is recommended, that is called as localized failure. If your beam fails, that can be easily restored. If your column collapses, then the entire structure will collapse. You can see this. If soft story failure occurs, the first image stands for the soft story failure. So the deformation is very, very little. When you come to the second image, you can see the deformation is very, very large, which means during an earthquake, plastic hinges were formed perfectly in the hinge locations. It allows the entire structure to deform gradually. So machine, it will come to its original position. So this is one of the important detailing procedure which is recommended in 13920. I told you that beam reinforcement should be anchored into the joint. You can see the horizontal part is the beam part and vertical element is column element. Now the reinforcement from the beam is perfectly anchored into the joint. If you go to any construction site, you can't see this kind of construction, because in actual construction, what we are doing, we are raising the column up to the beam bottom. We are raising the column up to the beam bottom. Then the reinforcement of the beam is inserted onto the column. In such case, the anchorage is not possible. According to our IS 13920, the recommended anchorage length is LD plus 10 times diameter of the bar. So LD is the anchorage length. We have to calculate as per IS standard plus 10 times the diameter of the bar. So the reinforcement from the top will go down and reinforcement from the bottom will go up. So this will provide the anchorage capacity to the beam. If you're not properly anchored the beam into the joint, the beam will come out from the joint during an earthquake. So this is called ductile detailing of the joint portion. So the vertical element is column portion and the horizontal element is the beam portion. So now you can see how the joint detailing is recommended in IS code. This recommendation is over a small length, not over throughout the column. You can see this image, they have mentioned as LO, which is the hinge length in the column. So up to this length, we have to go for closer stirrup spacing detailing, which will allow the entire structure to deform as well as to rotate during large deformation. If you don't have such a closer confinement, we can't confine the core concrete, so the core concrete will fail immediately after the formation of diagonal cracks. That's why our IS code recommends this kind of critical detailing in the joint region, as well as this is the potential hinge region of the frames. This is how we have to detail the beam as well as the foundation point, because I have clearly shown you in the image that plastic hinges will not form in the every column port except at the foundation level, because we are ensured that plastic hinge formation is occurring exactly below the column part, which is very close to the foundation. So that time our foundation part should be able to resist large amount of lateral force. That's why we are recommending the closer confinement in the foundation level. So these are the various detailing how that confinement should be made, that hooks inclination as well as the hook length, everything. Because if it is not providing that proper hook, what will happen when a large deformation occurs? The confinement will open. When the confinement opens up, what will happen? It can't confine the concrete. So immediately rupture will fail. So our IS code recommends, if you follow the IS code procedures, you can increase the ductility, stiffness behavior, inelastic behavior, energy dissipation. It will provide you a better damage tolerance capacity and offers better load resistance capacity and damping coefficient if you follow. Now, the question is, this is a recommended procedure to be followed in new construction. Suppose if I have a existing building which is not constructed by just using any codal procedure, then how can we ensure its seismic resistance? Then that's a very big question. So now we have many different techniques to improve the seismic resistance behavior of existing structure. So existing structure, we have a column, we have a beam, we have an infill, so we have foundation level. Now how to improve the performance? There are a lot of methods, conventional techniques, advanced techniques. So FRP strengthening is an advanced technique which will offer you a lot of advantages in improving the performance of the entire structure. And FRP means fiber reinforced polymer. It is available in various forms, and this FRP is taken from glass, which means they are using glass powders in polymerization to make glass FRP. Okay, next one is carbon. They are using carbon to make FRP. Basalt is a natural based rock. They are using basalt to take FRP. And silica. Silica is again a natural material. They are using the silica also in deriving FRP. So now this FRP is available in different forms, like in sheet forms, cloth forms, plate forms, rod forms, whatever the form you want, you can make. So now the figure shows that it is available in, this is the sheet form or fabric forms. The first one is GFRP, the second one is CFRP. So the GFRP always will be in white color and the CFRP will always be in black color. So this is another various forms. It is available, I told you, it is available in sheet forms, plate forms, rod forms. So now, after a detailed research across the world, now the GFRP rods are available, epoxy-based rods are available, carbon-based rods are available in required form, which means it is not only available in plain form, it is available in ribbed form also. So this is the FRP bars having good elastic modulus, tensile properties, but you can't bend and you can't deform the entire FRP into a stirrups. So our factories are already made stirrups in derived form and desired form. The last image stands for FRP stirrups. It is available in ready-made. You can go and buy and you can use in our RCC structure instead of stirrups. I told you this is that if you are not doing the detailing measures properly, so this kind of diagonal cracks will form in the joint. So I told you we have to preserve the joint, otherwise the joint will fail before it attains its desired capacity. So in such case, if you want to provide a very good resistance to the joint, then we have to use FRP strengthening. So this is how they are in the next image. You can see how they have pasted the FRP to improve the joint performance. This is a schematic diagram. So in our actual case, the vertical portion is nothing but column, the horizontal portion is beam. Over the beam, we have slabs. So slab as well as the complete confinement for the column. This is how it will look after strengthening. You can see a beam column joint in a research laboratory, how they have confined the column as well as the beam part, and they are testing under cyclic load. This is the various failures. When you do conventional test, or the conventional beam column joint completely fails, when you do the FRP strengthening, how the joint performance increases. You can see in the front image. So different type of FRP strengthening can be done with respect to the requirement, because we can't use FRP same method everywhere. In some joint may have higher strength, some joint may need lesser strength. So based on the requirement, we have to choose which methodology we have to adopt. So in this image, you can see different type of FRP strengthening. When you go for column to beam connection, we can go for L. And after that, because with respect to the L, it is perfectly anchored, but it is not perfectly anchored with the beam port or with the column port. The last image you can see, the L port has been perfectly anchored with the column as well as in the beam. So these are the various type of FRP strengthening in the beam column joint. Again, another various type of strengthening. So this is how it will look when you do FRP strengthening in RCC complete building. You can see the column is perfectly confined and beam is partially confined, because in beam you can't do the complete wrap. So the beam part will be perfectly wrapped in U shape and it will be anchored with the slab. whereas the column can be easily confined all around the. You can see in the image how the beam column joint has been strengthened using CFRP. So in FRP strengthening, FRP plays very important role. Apart from that, epoxy plays another important role. Epoxy is a binding agent which is being used to connect FRP and concrete structures. If your FRP fails, the entire structure will fail. That is separate. If your epoxy fail, the entire FRP strengthening scheme will fail. So choosing epoxy is very important, and epoxy can be chosen with respect to the technique and surface of your concrete and the type of your FRP, because glass fiber need different different epoxy, and carbon fiber need different FRP, basalt need different FRP. So based on the FRP, we have to choose different epoxy. A simple example how we are doing FRP strengthening in a joint. You can see this is an exterior beam column joint, and which area we have to strengthen, that has been identified. And first we have to rub the surface, and all the 4 corners should be smoothly curved. It should not have sharp edges. Otherwise, what will happen when you do FRP wrapping? The sharp edges will apply stress on the FRP. It will rupture. FRP is very flexible. You can make into any shape, but after applying with epoxy, it will become like a plastic. You can break it. FRP is very flexible. Once when you apply with epoxy, it will become rigid. It will become like a plastic. So it will easily get ruptured. So in this image, you can see the surface of the joint has been completely smoothened. Then they have applied a primer coating. Next, you can see the red color is nothing but, show the image. The red color image is nothing but, red color portion is the epoxy. So they have applied epoxy. Just by normal brush you can apply. Then next image, you can see 2 persons are applying CFRP sheet. Okay. After applying the CFRP, they are providing the last image. You can see after completing the retrofitting, it will look like this. Now your joint is restored. This joint is not actual joint. This is damaged joint, and it has been restored. After testing, how the FRP will fail. I told you FRP is a flexible one, but after epoxy, it will become rigid. So you can see this image. After testing under cyclic load to simulate the earthquake performance, you can see this image. So the FRP completely came out. Epoxy, that FRP, which was affixed on the column port, completely comes out. The reason is improper or inadequate anchorage. Your epoxy will play up to a certain limit. It will not go more than that. So if you want to increase the performance, we have to improve the performance of your epoxy. The strength between the bond strength between epoxy and FRP is very important. Otherwise, this kind of bonding failure will occur. Or otherwise, we have to use high modulus FRP, which means among the CFRP, GFRP, BFRP, carbon fiber has higher modulus capacity than all other FRP. If you use, because carbon fiber is costly, that's why another type of like glass fiber, basalt we are using. But if you use carbon FRP, this kind of failures can be avoided. Next one is beam. So previously we have seen beam column joint. Now beam. Your beam is a rectangular member or otherwise T-section. If you want to do FRP strengthening of your beam, it can be done in many ways. You can see a beam with internal confinement by the stirrups and external confinement provided by the FRP. We can do partially vertical and 90 degree vertical or with some 45 degree inclination. Whereas in the next image, you can see the completely it is wrapped. If you are doing complete wrapping, you have to provide adequate lap length between one part of FRP to another part of FRP. The first one stands for complete wrapping. The second one stands for FRP with adequate lap. The third stands for the individual strip wrapping. Because this kind of things will eliminate our your economical aspect. Because when you go for complete wrapping, we have to use large amount of FRP. It's very costly. When you go for individual wrapping, the cost is less, as well as it will give you the same amount of performance. You can see the conventional beam failure. The second one after FRP strengthening, the failure mainly focused in unstrengthened portion. Strengthened portions are very strong. Unstrengthened portions are fail. When you come to the third one, when you go for individual strip wrapping, this is how the failure occurs. And if you are not able to go for UWrap, UWrap means this is the beam, and if you go for UWrap, that's why we used to call UWrap. It is not recommended to go for UWrap always. When your required capacity is very, very small, then you can go for two-side plaster, two-side FRP of X. That's what it is shown in that image. Various type of FRP strengthening in beams and failures. And in this image, a T section has been strengthened using FRP with and without anchorage, which means end anchorage. The FRP, when you use in column, it can be completely wrapped. But when you go for beam, you can't completely wrap because of slab. So we used to go for U-wrap. When the entire beam deforms to a large extent, what will happen? The FRP will come out. That is generally referred as debonding failure, delamination from the surface. If your FRP delaminates, then we can't attain the entire strength, or the performance level is not attained. In such case, we have to provide end anchorage to the FRP. You can see in the third image, they have provided additional end anchorage in the all FRP strengthened part. So all the FRP strengthened beam with end anchorage has no evidence for delamination. When you go for FRP strengthening without end anchorage, you can evidence delamination. So this is how they are doing FRP wrapping in actual practice. So this is a carbon FRP. You can see that first they are applying the epoxy, then they are wrapping FRP all around the beam section. Next one is NSM technique. Suppose if my internal reinforcement is not adequate, I need to go for external reinforcement. External reinforcement can be done using FRP sheets. That's called FRP wrapping. Next one is near surface mounting reinforcement. I told you FRP is available in different forms. This is nothing but FRP strips or sheets or plate. So we have to groove the bottom portion, and we have to use epoxy or any adhesive to fill the grooved portion, and the FRP plates has to be inserted into the bottom. So this will act as a reinforcement, not like external confinement. This is different. This is internal reinforcement. We are providing externally. If your flexible capacity of your beam is inadequate, then we have to follow this kind of near surface mounting technique at the bottom of your, at the soffit of your beam, which will increase the tensile capacity of your beam externally. So additional factors to be considered during FRP strengthening is its anchorage, deflection. When you do FRP strengthening, you can't expect the beam to deflect large amount. It won't deflect because when you're fixing with some stiff material, it will increase the strength capacity than the deflection capacity. So you can see in this low dose deflection graph, when you don't have FRP, the deflection is very high. When you are using single layer of FRP, strength is increased. At the same time, amount of deflection is reduced. When you go for multiple layers, strength is increased large, but at the same time, deflection is also limited. So according to the requirement, we have to choose. If you want to increase strength as well as deflection capacity, we have to reduce the number of layers. Next one is column strengthening. When you do FRP strengthening to the column, that will increase the confining pressure from the external agent, which will increase the axial load carrying capacity of the column. Again, it is not required to go for complete wrapping. So according to the requirement, you can choose any kind of wrapping, partially wrapping or fully wrapping. So that is for a circular element. This is for rectangular element. The top and bottom portion has been confined because the top and bottom is nothing but the joint portion. The middle portion is normally confined because it has no large shear force element. That's why the top and bottom portion having large amount of FRP compared to the mid portions. Again, like near surface technique in beam, you can go for FRP strip in the column also, plus CFRP or GFRP strengthening. So this is how they are doing FRP strengthening in actual practice. First, the surface will be smoothened, then they will apply epoxy, then they are rolling the carbon FRP, any FRP. You can see this is a bridge element. The bridge, they are strengthening the column, which means the pier, by using FRP strengthening. Again, this is a beam, this is a column restored after complete collapse. The column is severely damaged, and they have restored the column, and then they have done FRP strengthening. And when you do like in the existing structure, we have calculated that the existing structure is not adequate to resist an earthquake. So we are going for earthquake resistant measures using FRP strengthening. Now the question is, when you increase the superstructure capacity, but when you are not increasing the substructure capacity, then the entire structure will collapse immediately. So when you are increasing the superstructure capacity, simultaneously we have to ensure that substructure capacity is also increased. Otherwise, there is no use of strengthening the structure. You can see the existing foundation level has been increased. Then increasing the foundation capacity because already they have strengthened the column using FRP. Now the strength of the column is very, very large as compared with the foundation. So you can see if you have multiple number of columns, you can go for joint foundation during retrofitting. Now it is a case study we have done. Whatever the failure you have seen, we have identified, we have created the failures in our laboratory, and then we have done the FRP strengthening. Using FRP strengthening and another method using another technique using rebar couplers. This rebar coupler is invented by us in our laboratory. We have made our own rebar couplers, and especially for retrofitting techniques, and it can be used for new construction also. You can see this image closely if you watch the image. Anybody, what you are seeing this image, can explain? What you are seeing in this image? Yes. Now we have technology to lift a masonry structure, a RCC structure, whatever the structure it may be. You can lift the structure. If your ground floor level is very, very lower than the road level, then what will happen? During the rainy season, your rainwater will enter into the house. So in order to address this kind of issue, now we have technology to increase the height of the building, or you can horizontally move the building from one place to another, which means not another means another location, certain offset within the region. So now when you have a capacity to increase the height of the building, you can easily lift the building. You can easily lift the building, damaged building. Okay, that's the meaning. That's why I'm showing this image. You can see nearly 1 meter, 2 meter increase is possible with the help of a new technology. Not only RCC structure, masonry structure also. The second image stands for horizontal movement from one place to another. So the second image. The reason why I'm telling, during an earthquake, I told you soft story failure is predominant. Soft story failure means the car parking failure. That's why. Okay. So the topmost stories are perfectly rigid, but the bottommost story is completely collapsed. In this case, what we can do, if you identified such kind of problems, rather than demolishing the building, you can lift the building up to a certain limit, and the buckled bar, these are the buckled failure, rebar buckling failure, which means without due to improper confinement, the buckling occurred. Now you can lift the building up to a certain limit, then you can curtail the bar, you can provide a new bar, or you can straighten the existing buckled bar, you can connect both the broken new bars, or you can provide new bars, you can connect the new bar with the old bar, you can use any technique. But in actual practice, what we have, this is how we are doing retrofitting. First, we will remove the reinforcement and we will provide external reinforcement by this. And it is very, very difficult to provide you the closure confinement with proper hooks. It is not possible. So they will do a rough steps confinement like this, and they will do the welding and they will do the concreting work. This is the conventional technique we have. This is generally referred as RCC jacketing. This is how it works. What will happen in this case? We have existing concrete column element size, say 300 by 300. After strengthening, it will become 400 by 400 bottom as well as in the top. But the joint is again 300 by 300. We are not increasing the capacity of the joint. So what will happen when you increase the cross-sectional dimension? We are increasing the dead load as well as its modulus capacity. So now the strengthened column is more stiffer than the topmost column. Again, the same failure will occur in the conventional jacketing. That's why we are using FRP strengthening. When you are doing FRP strengthening, you are increasing the capacity of the joint, capacity of the column, capacity of the beam without increasing the cross-sectional dimension. So this is called rebar couplers. This is a ready-made coupler which is available in the market called threaded couplers. If you want to use this coupler, it can't be used in retrofitting work. This kind of coupler is eligible or applicable only in the new construction. So edge of the reinforcement volume should be increased. Then the edge of the reinforcement will be threaded, and this threaded reinforcement will be used in your. You can connect any threaded bar using threaded coupler. This is another coupler which is being used in Japan very widely, and this is completely based on a grouting limit, which means they will connect two rebars using a coupler, and they will inject a special grout. This grouting strength will provide you adequate bond strength. This is another coupler. Here in our laboratory, we have developed our own couplers to connect two broken rebars. You can see this foundation having 4 columns, and all the 4 columns have failed like this. This is a buckling failure because we have made a weaker part in the bottom, and we have applied lateral loading. So the entire bottom of the column is completely failed, and we have addressed the buckling failure also. Now we have developed our own coupler like this, and we have removed all the 4 columns from the foundation. Second, this is how after removing. Second, you can see the buckled bar. Third, you can see how the buckled bar has been straightened. In actual practice, you may ask me, actual practice, it is not possible to completely remove the column. That's why I told you, in actual practice, you can raise the building. So you can cut the buckled bar or yielded bar. Then you can insert the coupler, you can easily connect. If you see the next image, you can see they are lifting and they are connecting with the couplers. So when you do like this, you can easily connect 2 broken bars, or you can additionally add a new bar with the broken bar. So in this case, now you can easily go for a closed confinement. You can insert the stirrups into the column section, and you can provide closer confinement. So this is how it will look after connecting the old part or the new part. Now we are filling with grout. Next, we have provided the closer confinement. Now this is a column which is connected with the foundation. Now the question is, the column portion has old concrete. When you do new concrete, and from the bottom to top, if you do a concreting like from bottom to top, there is a possibility of bond between old and new. Even whatever the advanced technology you can use, but still there is a possibility of shrinkage cracks between old and new when you do concreting for this. That's why we have done, we have applied a special epoxy on the old surface. Then we used a letterbox shuttering line. This shuttering is generally referred as letterbox shuttering. So when you fill concrete and when you lock like this, that will give you additional pressure. Now the concrete will touch the topmost surface, which is already applied with epoxy. So now the possibility of shrinkage cracks can be avoided or eliminated. So this is a retrofitted column. The bottom portion having new, and the topmost column is old concrete. You can't see any connection. Now we are applying epoxy and we are doing FRP strengthening. This is the column after strengthened. The first one is after retrofitting. Next we are applying epoxy, and third we have completed FRP wrapping. Now this is the quasi-static testing facility in earthquake engineering laboratory. You can see we have attached an actuator and we have tested the column, which is strengthened, which is not strengthened. This is control 1, and this is how the failure occurred. This is retrofitted with FRP strengthening with coupler. See the loop? Very similar kind of loop. If you see the strength, it is nearly 23 kilonewton. When you come to this case, it is 30 kilonewton capacity. Strength is increased. This is how the failure occurred. Because in the previous case, you can see the reinforcement is buckled. In the next case, due to FRP strengthening, the column rotates. Column rotates. That's why we have achieved 150 mm deflection without any reinforcement buckling failure or FRP rupture failure at the joint portion.
So can you explain the graphs that how this cyclic kind of behavior used to be there in case of quasi-static lab facility?
Okay, when you actually basically we have a testing facility that is called a quasi-static testing facility, which means reverse cyclic. We used to call as reverse cyclic. One is static. When you have a beam, like this, if you want to measure its load carrying capacity, and we have to apply a load like this, so the beam will deform. If you want to understand its behavior, we used to plot a graph between load as well as deflection. So you can get a graph like this. This kind of loading is generally referred as static. This is static loading. Next one is dynamic. We can't use dynamic for beam. For the dynamic, you have to use this kind of loading. So when you vibrate the platform, which is being supported with any structures, like this is called a shake table, and we have a constructed model like this. This shake table will be connected with some actuators. This actuator will give you horizontal shaking. Okay, so this is how the load will be applied to the structure. Now, the entire structure will collapse immediately after applying the load. So this is called dynamic loading. From this dynamic loading, you can understand how the failure will be. But if you want to watch the performance closely, you can't go for dynamic loading. We have to go for quasi-static, which means we are applying cyclic loading in a very slow rate. Like if I want to test a beam column joint, this is column part, this is beam. Now, you can apply some axial load like this to keep the column stable. Now, this particular beam will be connected with some actuator. This actuator will give you push, come to zero, then pull. So, what will happen? When you apply load to the beam will move like this. First, when you push, then when you pull it, again it will come to the zero position, then it will move. Similarly, we used to apply, this is called push and pull. This is called reverse cyclic load. In a very, very, very slow rate, which means less than 1 hertz. If you are applying cyclic loading less than 1 hertz, then generally that test facility is referred as quasi-static test, which will help you to identify or understand how the entire structure behaves. If you want to watch a performance, like if you shoot a particular bottle using a bullet, immediately the bottle will collapse. If you want to see the performance, you have to use slow motion camera to understand the behavior of failure. Okay. Similarly, if you want to understand the behavior of a joint or a beam or a column, we have to use quasi-static loading, which will apply lateral load in a very, very, very small rate, small displacement rate. So that will help us to understand the cyclic behavior. Now, in static testing, the output will be in the form of load versus deflection graph. Whereas in this kind of testing, the output will be in the form of loop. That loop is generally referred as hysteresis loop. When I apply loading like this, it will go like this. Okay? And up to, say, 10 mm deflection. And the load is 10 kN. Then I'm again pulling back. It will come to zero push. It will come to zero push. Then again I'm pulling. Again I'm stopping at 10 mm deflection. Again I'm pulling. So we are getting a loop. If I continue the test, it will going like this. This curve is generally referred as hysteretic curve. So what it helps, what it explains, actually, the area enclosed in the curve, is generally referred as energy dissipated during the time of loading. The amount of energy dissipated, which means during an earthquake, some amount of energy will be given to the structure in the form of earthquake force. The amount of energy will be absorbed by the building, it will be dissipated. The amount of energy applied, absorbed, and dissipated. It can be understood from this load. Here, this amount of energy is dissipated through the joint. It can be understood from the hysteresis loop. But basically, when you go for static testing, that will give you energy absorbed. This is the load deflection graph under static loading. So the energy under this entire graph will explain you the amount of energy absorbed by the structure, not dissipated. So this is the difference between static, dynamic, and quasi-static, which we have done. In this image, you can see this hysteresis loop explains you how the entire structure behaves, the amount of energy dissipated. And this is the failure. Thank you.